Good evening. Tonight on The Whispering Scientist, we're floating quietly into the vastness above, embarking on a calm, slow drift through the silent ocean of the cosmos. Wherever you are listening from, whether it's a city glowing faintly under clouded skies, or a quiet room where the night is still, welcome. I hope this exploration helps you unwind, clear the noise of the day, and fall gently into sleep among the stars. We begin our journey not with a bang, but with a breath, letting the scale and quiet elegance of the universe wash over us. If you're new here, I'd love to know where in the world you are watching from tonight. It's always a small wonder seeing this sleepy constellation of listeners scattered across the planet. And if you find this journey relaxing, please do tap that like button and subscribe. It truly helps the channel keep growing quietly, one curious mind at a time. To everyone already subscribed, thank you for being part of this calm little corner of the internet. So, as the night stretches out and the hum of the world fades, let's look upward. Out there in the deep dark, light has been traveling for billions of years just to reach your eyes. Have you ever wondered what stories those photons might tell if they could speak? Space is vast beyond comprehension. The numbers we use to describe it almost lose their meaning. Yet within that immensity lies a quiet elegance, a structure, a rhythm, and a pattern that connects everything from the smallest atom to the largest galaxy. In this calm exploration, we'll wander through the great expanse, allowing each cosmic idea to be a small truth, a tiny fragment of the universe's story. Together they form a tapestry of time, energy, and wonder. We'll drift from the silence between stars to the slow birth of galaxies, and from the hum of gravity shaping orbits to the faint cosmic afterglow left from the dawn of everything. This isn't a lecture or a test. It's a gentle, unhurried journey through space itself. You don't need to remember any of it. Just let the ideas pass by like constellations. Some will shine brighter, others will fade quietly into the dark, but all of them belong to the same vast night sky. So find a comfortable place and let curiosity do what gravity does best, draw you in, because even in the stillness of space, something beautiful is always happening. The vast and quiet universe is unlike anything we can truly imagine. When you think of space, you might picture stars glittering like distant lanterns or planets slowly circling their suns. But the most defining feature of the cosmos, the element that makes all else possible, is its profound silence. On Earth, sound is part of every moment. The wind in the trees, the hum of traffic, even the quiet rhythm of breathing. Sound, however, is nothing more than a vibration moving through matter. And in the emptiness between stars, there is almost no matter at all. The vacuum of space has so few particles that the waves which carry sound on Earth simply cannot travel there. If you were to shout in open space without a radio, your voice would vanish instantly into nothingness, never to be heard. The only communication that exists is through the electromagnetic waves, light, radio, and X-rays, that travel through the void, whispering stories of distant worlds to our instruments back home. It is in that silence that we find a scale beyond comprehension. The part of the cosmos we can currently observe stretches roughly 93 billion light-years across. That number alone is almost too big for the human mind to grasp. To measure this, we use the light year, which is the distance light travels in a single year, nearly 10 trillion kilometers, and the observable universe is filled with light that has been moving across that distance for billions of years. We call it observable because it represents the sphere of space from which light has had time to reach us since the universe began. Beyond that limit, there may be infinitely more stars, galaxies, perhaps even entire cosmic structures, but their light hasn't yet arrived. Every night sky is, in a way, a horizon of time as much as it is of space. When astronomers say the universe is about 13.8 billion years old, they're describing the time since space itself began expanding. Before that moment, there was no space in which to expand, no time to measure. It all began in an instant of unimaginable density and heat, a cosmic beginning that was neither an explosion in space, but rather an expansion of space. From that first instant, the universe has been growing ever since. Light from the earliest stars and galaxies still travels through the darkness, stretched thinner and redder as it goes, a fossil record of ancient brilliance. Every photon we capture from the edge of the observable universe began its journey when the cosmos was young, long before Earth, the Sun, or even our galaxy existed. In that sense, when we study the stars, we're also studying the past, watching history unfold not in books but in beams of light. As the universe expanded, it began to take shape in surprising ways. On the larger scales, matter doesn't spread evenly like a smooth fog. Instead, it forms an intricate pattern of filaments and voids, sometimes called the cosmic web. Galaxies are not scattered randomly. They gather along vast, invisible threads of dark matter, separated by immense gaps where almost nothing exists. Even in the places we call filled, space remains overwhelmingly empty. The average density of the universe is so low that if you took all the matter and spread it evenly through space, you'd have only a few atoms per cubic meter. It is hard to picture an emptiness so complete, yet it's within that emptiness that all the beauty we see is suspended. Galaxies glow faintly like lanterns hung across an infinite sea of nothing. The silence, the vastness, and the emptiness all work together to create a cosmos that is both fragile and enduring. The stillness between the stars is not a void to be feared, but the necessary stage upon which everything else can exist. The quiet of the universe also has a kind of poetry. Every particle, every photon, and every tiny spark of energy has been moving through that stillness since time began, untouched by air, water, or stone. When a star explodes, the shock wave expands into a vacuum so pure it barely stirs. When two galaxies collide, they pass through one another with almost no friction, their stars drifting silently past in slow gravitational dances. In a universe full of motion, sound plays no part, and so it is through light that we listen. Telescopes become our ears, and wavelengths become the music of the cosmos. If space seems lonely, it's worth remembering that everything we know, every atom in your body, every sound you've ever heard, was once part of that same silence. The elements that form your bones and your breath were made in stars that burned out long before our planet existed. Their light still crosses the void, and their dust still drifts between galaxies. In this way, the universe is both vast and intimate. The same emptiness that separates stars also deeply connects us to them. So when you look up at the night sky and see that darkness stretching endlessly outward, you're not looking into nothing. You're looking into the largest structure we can conceive, a silent, ancient, and beautifully balanced expanse where time, light, and gravity weave the pattern of existence itself. The vast and quiet universe is not empty after all. It is full of potential, memory, and the faint hum of everything that ever was and ever will be, carried silently through the dark. Light and distance are inseparable when you begin to explore the universe. Every glimmer you see above you is both a measure of how far away something is and how long its light has been traveling to reach you. When astronomers talk about vast distances, they rarely use kilometers or miles. Those familiar units crumble under the sheer scale of the cosmos. Instead, they use the light year, the distance that light can travel in a single year, which is about $946 trillion kilometers. Imagine light as the fastest messenger in existence, racing through the vacuum at nearly 300,000 kilometers every second, never stopping, never slowing. Even at that staggering pace, it would take more than 4 years to reach the nearest star beyond the Sun, and tens of thousands of years to cross our galaxy. The light year isn't just a measurement of distance. It's a fundamental reminder that space and time are woven tightly together. Every point of light in the night sky is a little time capsule, a record of where that object was when its light began the long journey toward your eyes. That's why looking farther into space also means looking further back in time. When you gaze through a telescope at a distant galaxy, you're seeing it not as it is now, but as it was millions or even billions of years ago. The light that paints its image traveled across expanding space, unspooling its story, photon by photon. This isn't an abstract concept. It's literal. The Andromeda Galaxy, the nearest large spiral to the Milky Way, lies about 2 million light-years away. The glow we see tonight left that galaxy before modern humans existed on Earth. When astronomers use powerful telescopes like Hubble or the James Webb, they're not just peering across distance. They're witnessing the universe as it once was, studying galaxies that formed when the cosmos was young and the first stars were igniting. The farther we look, the older the universe appears, until we reach the faint afterglow of the Big Bang itself, light that has been traveling for nearly the entire age of time. The reason we can use light as a ruler for both space and time is that its speed is constant. In the vacuum of space, light always moves at about 299,792 kilometers per second. No matter where you are or how fast you're moving, that number doesn't change. It's one of the fundamental laws of nature, a cosmic speed limit that nothing with mass can break. Even gravity obeys it because changes in the gravitational field travel as ripples, gravitational waves, that also move at the speed of light. This constancy is what makes Einstein's theory of relativity possible. It means that time and space must bend and stretch to preserve that speed, so that light always races along at the same pace. When we measure distant stars or galaxies, we trust this rule absolutely. Every photon we collect has spent a fixed amount of time on the road, and from that we can tell how far it has come. Starlight itself is a beautiful witness to these scales. The glow from nearby stars may have left them only a few years ago, but the faint light of distant galaxies began its journey when dinosaurs still walked the Earth, or even before Earth had formed at all. Some of the light entering your eyes tonight has traveled for billions of years, untouched, crossing the cold, dark spaces between clusters of galaxies, bending slightly through the pull of gravity until it found our small blue planet. When you realize that, the night sky feels both humbling and intimately close. Every point of light is a story from the past, traveling silently through time so we can know that it existed. The stars overhead are not shining now. They shone long ago, and we're only just seeing the evidence. The sky is a living fossil record, written in photons, but those photons don't always arrive in their original color. The farther a galaxy is, the more the space between it and us is stretched during the light's journey. This stretching changes the wavelength of the light, shifting it toward the red end of the spectrum, a phenomenon known as redshift. It's not that the galaxy itself is moving through space in the usual sense. Rather, space itself is expanding and it carries the light with it, like dots drawn on a balloon as it inflates. The more the universe expands, the more the wavelengths lengthen and the redder the light appears. By measuring how much a galaxy's light has been redshifted, astronomers can calculate not only its distance, but how fast the universe is expanding. This discovery reshaped cosmology, revealing that the cosmos isn't static or eternal. It's dynamic, growing, and changing. What we see in the deep sky is a snapshot of that motion, frozen in time. Light and distance together form the language of astronomy. Through them, we read the universe as it writes its history across space. The numbers may seem immense, trillions of kilometers, billions of years, but each measurement connects directly to what we can see with our own eyes. When you trace a beam of starlight backward, you trace the story of space itself. You glimpse the moment a photon was born in a star's core, perhaps scattered through a nebula or deflected by galaxies before finding its way here. The speed of light, constant and finite, transforms every observation into a meeting with the past. And as the universe continues to expand, That light keeps stretching, redder and fainter, a soft echo fading into infinity. The next time you look up at the stars, imagine the distance between you and them, not in kilometers or miles, but in years of light. Think about the time that has passed since each beam began its journey, the civilizations that have risen and fallen, the stars that have lived and died in between. In that quiet glow, you are witnessing both the vastness of space and the persistence of light itself. The night sky is a bridge across time, and every photon that reaches you is proof that even across unimaginable distances, the universe still finds a way to be seen. Galaxies, clusters, and superclusters make up the grand architecture of the universe, a cosmic cityscape where each galaxy is a glittering metropolis of stars. Our own home, the Milky Way, is a barred spiral galaxy, a vast rotating disk about 100,000 light-years across. From the side, it would appear thin and flat with a bright bulge at the center and graceful spiral arms curling outward like the whorls of a seashell. From above, it would resemble a glowing pinwheel turning slowly through space once every 200 million years. Within those arms are hundreds of billions of stars, each with its own planets, moons, and stories. Between the stars, enormous clouds of gas and dust drift, giving birth to new suns, while others die and scatter their ashes back into the galactic sea. A bar of older reddish stars crosses the Milky Way center like a glowing bridge, where gravity and motion shape the galaxy's rhythm. And at the very heart of it all lies a supermassive black hole, Sagittarius A/M, a dark anchor weighing millions of solar masses, holding the galactic core in its invisible grip. The Milky Way is not alone. It belongs to a small cosmic neighborhood called the Local Group, a community of over 50 galaxies bound together by their shared gravity. Most of these are small and faint dwarf galaxies, like the Magellanic Clouds visible from the southern hemisphere, irregular, hazy smudges of light orbiting our galaxy like satellites. The second major member of this group is the Andromeda Galaxy, a magnificent spiral even larger than the Milky Way, lying about $2.5 million light-years away. Though that distance seems enormous, Andromeda is actually on a slow-motion collision course with us. In about 4 billion years, the two galaxies will meet, their stars passing through one another almost without contact as their mutual gravity reshapes them into a single, larger, elliptical galaxy. For now, though, they drift peacefully in space, moving closer at about 110 kilometers per second, a cosmic waltz set to a time scale beyond imagination. The Local Group itself is only a small corner of a much larger structure, the Virgo supercluster. This immense region spans more than 100 million light-years and contains thousands of galaxies arranged into clusters and filaments. Our Local Group sits on one of the smaller threads, slowly being drawn toward the Virgo cluster at its center, a vast congregation of galaxies about 55 million light-years away. The Virgo supercluster acts as a gravitational basin, gathering galaxies like leaves in a slow cosmic eddy. Beyond it lies an even greater structure called Laniakea, meaning immense heaven in Hawaiian, which encompasses the Virgo supercluster and many others. It's part of the vast cosmic web that stretches across the universe, where gravity and dark matter weave galaxies together into interconnected filaments. In that grand pattern, our Milky Way is just one bead on a thread that loops and curves through space. At smaller scales, galaxies tend to gather into clusters, tight groups held together by gravity and, surprisingly, by something invisible. These clusters are some of the largest gravitationally bound objects in the universe, each containing hundreds or even thousands of galaxies. The space between them isn't empty. It's filled with thin, hot gas that glows in X-rays, as well as the mysterious scaffolding of dark matter that provides the mass needed to hold them together. Without dark matter's invisible pull, the galaxies in a cluster would simply drift apart. We can't see dark matter directly, but we can watch how it bends light from distant objects through a process called gravitational lensing, creating arcs and distortions in the images we capture. Through those cosmic fingerprints, we can trace the hidden framework that shapes everything we see. Within these clusters and groups, galaxies live complex lives. They are not static, isolated islands. They move, interact, and sometimes collide. When two galaxies pass close to one another, their mutual gravity stretches and distorts them, pulling out long tails of stars and gas. Some of these interactions are gentle, like dancers brushing hands. Others are violent merges that can completely change a galaxy's shape. Spiral galaxies can become elliptical after a major collision, their ordered disks collapsing into smoother, rounder forms. These encounters can also ignite bursts of star formation as gas clouds are compressed and shocked into creating new stars. Over cosmic time, this cycle of meeting, merging, and reshaping has sculpted the galaxies we see today. Even the serene spirals that adorn astronomical images bear the marks of past encounters, subtle asymmetries, faint streams of stars, and hidden scars left by ancient collisions. All of this cosmic motion unfolds across timescales that make human history seem like a blink. Galaxies take hundreds of millions of years to complete a single rotation, and clusters evolve over billions of years. Yet despite the immense scale, there is a kind of calm order to it all. The same gravitational forces that shape an apple's fall also sculpt the dance of galaxies. The Milky Way's stars move together in a great steady flow, each orbiting the center while carrying its own family of worlds. The smaller galaxies around us circle like companions in a slow, endless ballet drawn by invisible threads of gravity. When we step back and look at this vast architecture, what's most astonishing is how connected it all is. From the smallest star cluster to the largest supercluster, everything belongs to the same cosmic hierarchy. Galaxies gather into groups, groups form clusters, clusters link into superclusters, and those superclusters form part of the cosmic web stretching beyond our ability to see. It's a pattern that repeats fractal-like across scales of unimaginable size. And though most of the universe is made of dark energy and dark matter, things we barely understand, the galaxies themselves give it shape and light. If you could see the universe from far enough away, you might notice that galaxies are not randomly scattered at all. They trace out filaments that snake across space like glowing rivers separated by enormous empty voids. The Virgo supercluster is just one knot in that cosmic tapestry, one luminous patch in the grand design. Our Milky Way, nestled on a small arm of that structure, is a single point of light among billions. Yet within that point lies everything we know, our history, our future, and the consciousness that allows us to look outward and wonder. The universe builds its beauty from repetition, from connection, from the quiet pull of gravity linking galaxies into a vast, intricate web. And though we may seem small within it, every act of looking upward ties us back into that same network, reminding us that we too are part of the grand design. The expanding universe is one of the most beautiful and mind-bending discoveries in all of science. For most of human history, people imagined the cosmos as something fixed and eternal, a grand celestial dome with the stars pinned in place. It wasn't until the early 20th century that a quiet revolution began. When astronomer Edwin Hubble aimed his telescope toward distant galaxies, he found that almost every one of them was moving away from us, and that the farther away a galaxy was, the faster it appeared to recede. This simple but astonishing observation revealed a fundamental truth. Space itself is stretching. The galaxies aren't flying through the void like debris from an explosion. Rather, the very fabric of space between them is expanding, carrying them apart. Hubble's discovery, made using a 100-inch telescope on Mount Wilson in the 1920s, reshaped our understanding of the cosmos. What had seemed timeless and static was suddenly alive with motion, an unfolding story rather than a finished painting. When space expands, it does more than just push galaxies apart. It also stretches the light that travels through it. As light waves journey across growing space, their wavelengths lengthen, shifting toward the red end of the spectrum. This cosmological redshift is a kind of time signature written on every photon. The redder the light, the farther and longer it has traveled, and the more the universe has expanded during its voyage. Imagine drawing a wave on a balloon, then inflating it slowly. The wave stretches, its peaks move apart, and its color would shift if it were light. Astronomers read these redshifts the way historians read old documents. Each one tells a story about how fast space was expanding when that light began its journey. It's through this gentle stretching of light that we can trace the universe's growth, measure its age, and even predict its fate. If we reverse this expansion in our minds, run the cosmic movie backward, we arrive at a time when everything was closer together, hotter, and denser. The early universe was a seething, luminous fog of energy and particles expanding at an incredible rate. Within the first few minutes, it cooled enough for protons and neutrons to fuse into light elements like hydrogen and helium, setting the chemical foundation for everything to come. For nearly 400,000 years, the cosmos remained opaque. Light scattered endlessly off free electrons, unable to travel far. Only when the universe cooled further did those electrons settle into atoms, allowing light to move freely for the first time. That ancient light still fills the sky today as the cosmic microwave background, a faint afterglow from a time when the universe was just a few 100,000 years old. From that blazing birth onward, expansion never stopped. It simply slowed, allowing matter to clump into stars and galaxies. For billions of years, gravity worked to counter this expansion. Galaxies formed, clusters grew, and cosmic structures took shape. Many scientists once assumed that gravity would eventually halt the expansion altogether, perhaps even causing the universe to collapse back in on itself in a big crunch. But in the late 1990s, two teams studying distant supernovae found something unexpected. The expansion wasn't slowing, it was speeding up. The universe was accelerating, as though some unseen force were pushing galaxies apart, faster and faster. This mysterious pressure pushing the universe apart became known as dark energy. No one yet knows exactly what it is. It could be an inherent property of space itself, or something even stranger, but it dominates the universe, accounting for roughly 70% of its total energy. The discovery of dark energy was as startling as Hubble's original revelation, reminding us once again that the cosmos refuses to be simple. Even now, it's evolving, changing, and stretching in ways that constantly challenge our understanding. Yet despite all this outward motion, not everything is swept away by the expansion. On smaller scales, gravity still reigns supreme. Within galaxies, the pull of mass binds stars and planets together. Our solar system isn't getting larger. The distance from Earth to the Sun stays constant because the Sun's gravity overwhelms the feeble tug of cosmic expansion. The same is true for galaxies within clusters. Their mutual attraction keeps them close, even as the space between those clusters grows. You might imagine the universe as a loaf of raisin bread baking in the oven. As the dough rises, the raisins move apart, but the raisins themselves don't expand. Each galaxy or cluster is like a raisin, dense and cohesive, while the dough, the fabric of space, stretches between them. This delicate balance between gravity and expansion defines the shape of everything we see. The galaxies, the filaments of the cosmic web, and the vast voids between them all reflect the interplay of these two cosmic forces. Over time, gravity builds structure while expansion smooths it out, stretching the distances between islands of matter. The result is a universe that looks both stable and restless, a grand pattern frozen in motion. Every photon of light carries a record of that dance, stretched by expansion, bent by gravity, and preserved across billions of years. When you step back to take it all in, The idea of an expanding universe is more than a scientific fact. It's a story about impermanence and growth on the grandest possible scale. The galaxies drifting apart are not signs of isolation, but of evolution. The space between them is not emptiness, but potential, expanding to make room for whatever comes next. Somewhere out there, new galaxies are forming, their light just beginning a journey that will take billions of years to reach us. And as that light travels, space will continue to stretch. Time will continue to unfold, and the universe will go on expanding quietly, endlessly into the unknown. The birth of stars begins in the quietest and darkest corners of the galaxy. These regions, called molecular clouds, are enormous and cold, stretching across dozens or even hundreds of light years. Within them, the temperature can drop to just a few degrees above absolute zero. At that chill, atoms of hydrogen, the simplest and most abundant element in the universe, move slowly enough to stick together, forming vast, invisible oceans of gas and dust. From afar, these clouds appear as dark blotches against the brighter backdrop of the Milky Way, but inside them, slow changes are underway. Gravity, ever patient, begins its quiet work, tugging gently on clumps of gas until they start to gather. Most of the time, these clouds remain stable for millions of years, supported by internal pressure and magnetic fields. But when something disturbs the balance, a nearby supernova, the shock wave of a passing star, or even the collision of two clouds, certain regions collapse. A new generation of stars begins to form in the darkness. As gravity draws the gas inward, the collapsing material starts to spin. Conservation of angular momentum ensures that as the cloud shrinks, it spins faster, like an ice skater pulling in their arms. The compression heats the gas, and the center grows dense enough to trap energy. Eventually, this central knot, called a protostar, becomes hot enough to shine faintly in infrared light hidden from our eyes, but visible to telescopes that can see through the dust. Inside its core, pressure and temperature rise until hydrogen atoms begin to fuse into helium, releasing energy in the form of light and heat. This marks the star's true birth, the moment it begins to shine from within. What began as a cold, invisible cloud becomes a source of light that can burn for billions of years. Each star is essentially a controlled thermonuclear engine, perfectly balanced between the inward pull of gravity and the outward push of radiation. Around these newborn stars, the remaining gas and dust don't simply vanish. They flatten into rotating disks. These disks, called protoplanetary disks, are where planets are born. Within them, tiny dust grains collide and stick together, forming pebbles, then boulders, and eventually the seeds of planets. Over millions of years, these fragments grow into rocky worlds and gas giants, moons and comets, all orbiting their parent star. Our own solar system was once such a disk, swirling around a young sun about $4.5 billion years ago. Evidence of this ancient process still lingers in the asteroids and icy comets that roam its edges. The story of star formation, then, is also the story of planetary birth. Every time a star is born, there's a chance that somewhere in the dust and gas around it, a world like ours might take shape. If you could look into a stellar nursery, the kind found in regions like the Orion Nebula, you'd see a breathtaking sight. These regions glow in soft shades of pink, blue, and violet, lit by the ultraviolet radiation of young stars. The gas, once dark and cold, becomes illuminated, sculpted into towering columns and swirling shapes by stellar winds. Astronomers call these places stellar nurseries for good reason. They're cosmic cradles full of stars in every stage of infancy. Some are still cocooned in dense gas. Others have already cleared away, their surroundings shining freely into space. The colors we see in the images captured by telescopes aren't just for beauty, they reveal the physics of the clouds themselves. Hydrogen glows red, oxygen blue-green, and sulfur soft orange. Each hue marks a different chemical fingerprint. Together they form some of the most stunning natural artworks in the universe. The famous pillars of creation, for example, are part of such a nursery, where stars are forming inside towering columns of dust several light years tall. Despite their beauty, these nurseries are turbulent places. As new stars ignite, they send powerful streams of particles, stellar winds, rushing outward at hundreds of kilometers per second. These winds carve out bubbles and cavities, compressing nearby gas and sometimes triggering new waves of star formation. Magnetic fields also play a vital role in regulating how stars form. They thread through molecular clouds, guiding the flow of gas and resisting collapse in some regions while aiding it in others. Too strong a field, and star formation slows. Too weak, and clouds collapse too quickly, forming clusters of short-lived stars. The balance between gravity, turbulence, and magnetism determines how efficiently a cloud can turn its gas into stars. In some galaxies, this process happens rapidly, giving rise to dazzling starburst regions where thousands of stars form in just a few million years. In others, it proceeds gently, one star at a time. Star formation is a constant act of renewal in the universe. While individual stars live for billions of years, the galaxies that contain them would fade without new ones being born. Each generation of stars enriches the cosmos, fusing simple hydrogen and helium into heavier elements, carbon, oxygen, iron, that are later dispersed by stellar winds or supernova explosions. These elements mix back into the interstellar medium, seeding the next generation of stars and planets. In this way, the universe recycles itself endlessly. The atoms in your body, carbon from old stars, calcium from supernova, iron from dying giants, were all forged in this ancient process. Every heartbeat, every breath you take carries the signature of a star that lived and died long before the sun was born. From a distance, the formation of a star might seem violent, gravity crushing gas, nuclear fires igniting, and winds tearing through clouds. But within that chaos lies an exquisite balance. The same physics that governs a collapsing cloud of gas governs the balance of forces in your own cells. It's a reminder that the universe, for all its vastness, is deeply connected. The next time you look up at the night sky and see a single point of light, remember that it was once just a faint flicker deep within a cold cloud, waiting for gravity to nudge it into life. That quiet process, repeated trillions of times across billions of years, is what fills the darkness with stars. And somewhere, even now, in a hidden corner of the Milky Way, another one is just beginning to shine. The lives of stars are written by their mass. From the moment a star is born, the amount of material it gathers decides nearly everything about its future: how hot it will burn, what color it will shine, and how long it will live. Massive stars live fast and die young, burning through their fuel in mere millions of years. Smaller stars, on the other hand, lead long, quiet lives, glowing steadily for billions or even trillions of years. The physics is elegantly simple. The more mass a star has, the greater its gravity, and the more intense the pressure and heat at its core. That higher temperature drives faster nuclear fusion, making the star brighter, but also exhausting its hydrogen supply much sooner. A giant blue star might outshine the sun by tens of thousands of times, yet it will fade away long before a modest yellow star like ours reaches middle age. In contrast, the smallest stars barely glow at all, but they have the patience of eternity. The most enduring of these small stars are the red dwarfs, tiny, cool suns that burn their hydrogen with remarkable thrift. They make up the vast majority of stars in the Milky Way, quietly shining in red and orange hues, too faint for the naked eye to see. Their surface temperatures are much lower than the sun's, and they fuse hydrogen so slowly that their lifetimes stretch to extraordinary lengths. Some are predicted to last not just billions, but trillions of years, far longer than the universe itself has existed. None have yet reached old age because the cosmos is still too young for that. Even the first red dwarfs formed over 13 billion years ago are still burning steadily. Around these stars, planets may orbit for epochs longer than the age of all human history multiplied countless times. When the larger, brighter stars have long since gone dark, it will be the red dwarfs that keep the universe softly glowing in the far future, guardians of the long cosmic night. Our own sun sits somewhere in the middle ground, a typical medium-mass yellow star. It spends the majority of its life in what astronomers call the main sequence, the long, stable phase where hydrogen is fused into helium in its core. This delicate balance between gravity pulling inward and radiation pushing outward defines most of a star's existence. For the Sun, this stage lasts about 10 billion years, and we're currently a little less than halfway through that span. During this time, the Sun remains remarkably steady, producing the consistent light and warmth that have allowed life to flourish on Earth. The stability of main sequence stars like the Sun is a quiet miracle of physics. For billions of years, the same processes repeat with astonishing precision, maintaining the perfect equilibrium between collapse and explosion. This is why planets like ours can orbit for eons without fear of sudden chaos, but stars do not last forever. As hydrogen runs low in the core, fusion slows and gravity begins to gain the upper hand. The star contracts under its own weight, heating the core even further until it becomes hot enough to start fusing helium into heavier elements like carbon and oxygen. The outer layers respond to this new burst of energy by expanding dramatically. A star that once shone modestly in yellow can swell into a red giant, growing hundreds of times its original size. If the Sun were to expand that way today, its outer edge would engulf Mercury and Venus, and perhaps even reach Earth's orbit. These red giants glow cooler on the surface, giving them their deep reddish hue, but inside they are cauldrons of fierce nuclear reactions. The transformation marks the final act of a stable star's life, a period of beauty and instability before its final fade. Some stars, particularly those near the end of their fuel supply, behave unpredictably even before they reach that stage. Variable stars are celestial rhythm keepers, brightening and dimming over precise intervals. Their pulsations are caused by changes in their outer layers, expanding and contracting as heat builds and releases. These cycles can range from hours to months, but each is consistent. So consistent, in fact, that astronomers use them as cosmic measuring sticks. One type, known as Cepheid variables, helped reveal the true scale of the universe. When Henrietta Swan-Leavitt discovered the relationship between a Cepheid's brightness and its period in the early 1900s, she gave astronomers a tool to measure distance across the cosmos. By observing how quickly a variable star brightens and fades and comparing its apparent brightness to its intrinsic one, we can determine how far away it is. The technique allowed Edwin Hubble to prove that other galaxies lay far beyond our own, expanding the known universe from a single island to a cosmic ocean. These rhythmic stars remind us that even in apparent stillness, the universe pulses with life. Each variation in brightness is a reminder of the dynamic nature of stars, objects that seem eternal but are always changing. Some variables are binary systems where two stars orbit so closely that one occasionally eclipses the other from our point of view. Others are unstable giants, swelling and shedding material as they evolve. Their light flickers like a heartbeat, marking the passage of cosmic time. In studying them, we learn not only about distance, but about the internal structure of stars, the delicate balance of pressure, temperature, and gravity that keeps them shining across their vast lifetimes. Stars live through cycles of creation, stability, transformation, and decline. Their mass writes their fate, but their light writes the universe's story. The smallest red dwarfs may live for trillions of years, while the most massive blue stars burn out in a flash of brilliance. In between lie countless others, orange dwarfs, yellow suns, and red giants, all playing their part in the grand stellar symphony. From the moment they ignite to the moment they fade, stars are engines of transformation, turning simple hydrogen into the elements that build planets, oceans, and living beings. Every atom of calcium in your bones, every bit of iron in your blood, once passed through the heart of a star. The lives of stars are the lives of everything else, and in their light, the story of the universe continues to unfold. The story of a star's life always ends in transformation, not destruction. When a star has exhausted the last of its nuclear fuel, the delicate balance between pressure and gravity begins to collapse, and what follows depends entirely on its mass. Small and medium-sized stars, the quiet, steady ones, like our Sun, end their lives with remarkable grace. When their core fuel runs out, the outer layers swell into a red giant, glowing softly against the blackness of space. The surface grows cooler while the interior becomes unstable, and the star begins to shed its outer layers into space. Over thousands of years, those layers drift outward, forming a glowing shell of gas known as a planetary nebula. The name is misleading. It has nothing to do with planets. But when early astronomers saw these delicate rings and bubbles through their telescopes, their round shapes reminded them of distant worlds. In truth, they are the fading sighs of dying stars, beautifully illuminated by the light of what remains inside. At the center of each planetary nebula lies the star's bare core, a small dazzling ember called a white dwarf. Though only about the size of Earth, it contains a mass comparable to the Sun. This means that a teaspoon of white dwarf matter would weigh several tons. It no longer burns fuel or undergoes fusion. It simply glows with the leftover heat of its past life, gradually cooling over billions of years. The atoms inside are packed so tightly that electrons form a kind of pressure known as electron degeneracy, which holds the core up against further collapse. Over unimaginable time scales, white dwarfs will eventually fade into black dwarfs, cold, dark remnants adrift in space. None yet exist, because the universe is still too young for any white dwarf to have fully cooled. For now, they continue to shine faintly, a quiet reminder of the stars they once were. For the more massive stars, however, the ending is far more dramatic. These giants burn through their fuel rapidly, creating heavier and heavier elements in their cores: carbon, oxygen, silicon, and finally, iron. Iron marks the end of the road because it cannot release energy through fusion. When a star's core fills with iron, fusion stops and gravity wins. In less than a second, the core collapses inward, compressing to densities so high that protons and electrons combine into neutrons. The outer layers, suddenly without support, crash down and rebound in a titanic explosion, a supernova. For a few weeks, the light from that explosion can outshine an entire galaxy. It is one of the most powerful events in the universe, a brief and magnificent end to a long stellar life. In that explosive moment, the star gives back everything it ever created and more. Supernovae are the universe's great forges, the places where the heaviest elements are made: gold, platinum, uranium, and even the calcium in your teeth. All of it was born in the heart of a dying star. The shock wave from the explosion blasts these newly created elements into space, mixing them into the interstellar medium, where they'll one day become part of new stars and planets. This cosmic recycling ensures that every generation of stars enriches the next, slowly turning the universe from a simple place of hydrogen and helium into one filled with complex chemistry and the ingredients for life. When you wear a gold ring, you're wearing a piece of a star that ended in a supernova billions of years ago. The fate of what's left behind depends again on mass. If the collapsed core is between 1.5 and about 3 times the mass of the Sun, it becomes a neutron star, a sphere barely 20 kilometers across, but so dense that a single teaspoon of it would weigh billions of tons. Neutron stars spin rapidly, sometimes hundreds of times per second, and emit powerful beams of radiation. When one of these beams happens to sweep past Earth, we see a regular pulse of light, a pulsar. They are cosmic lighthouses marking the graves of massive stars while helping astronomers test the laws of physics under conditions that can't be reproduced anywhere else. In some cases, two neutron stars orbit each other, spiraling closer over millions of years until they finally collide, releasing a burst of energy so intense it ripples through space-time itself as gravitational waves. These collisions also forge some of the rarest elements in the universe, continuing the cycle of creation even in destruction. If the core is even more massive, not even neutron pressure can halt the collapse. The matter falls inward without limit, compressing into a point of infinite density, a black hole. Around it, space and time warp so extremely that not even light can escape its grasp. The boundary of this invisible trap is called the event horizon, and beyond it, the star's past life becomes forever hidden from view. Black holes are not cosmic vacuums. They don't roam the galaxy, swallowing everything in sight. Most of the time they sit quietly, their immense gravity only affecting nearby gas or stars that wander too close. But when material does fall into them, it heats up and emits powerful radiation as it spirals inward, producing some of the brightest sources of energy in the universe. Though the processes differ, from gentle fading to cataclysmic explosion, the endings of stars are moments of profound renewal. Every stellar death reshapes its surroundings, sowing the seeds for future generations of stars and planets. The elements scattered by supernova drift for millions of years before gathering again into new clouds, new suns, and new worlds. The atoms that make up your body, your breath, and the air you exhale were all once part of such a cycle, forged in a star that lived and died long before our solar system formed. In that sense, the death of a star is never truly an ending. It's a passage, one that links the quiet beginnings of hydrogen clouds to the complex chemistry of life. In the end, the universe is built on these acts of transformation. Some stars fade gently, others die in fire, but all contribute to the continuing story of creation. The next time you see the soft glow of a nebula or a distant point of starlight, you're looking at both the past and the future, the ashes of ancient suns and the raw material for those yet to come. Every night sky is a reminder that endings in the cosmos are never final. They're simply the beginning of something new. Our sun is an ordinary star with an extraordinary role. Classified as a G-type main sequence star, it has spent about $4.6 billion years quietly converting the simplest element in the universe into light and warmth. G-type speaks to its surface temperature and color, soft yellow-white rather than the brilliant blue of massive, short-lived stars or the deep red of cooler dwarfs. Main sequence means it is in the long, stable middle chapter of stellar life where gravity pulling inward and radiation pushing outward are perfectly balanced. That steady equilibrium is why our seasons and climate have had time to nurture oceans, continents, and life. Inside, the sun is layered. There is a hot, dense core where fusion happens, a radiative zone where energy zigzags outward as photons are repeatedly absorbed and re-emitted, and a convective zone where great cells of hot plasma rise and cool gas sinks like a slow-motion, star-sized pot of simmering soup. The visible surface, the photosphere, is only a few hundred kilometers thick, paper-thin compared with the sun's size. Yet, it is our window into the restless physics beneath. Every second, the sun performs an astonishing act of alchemy, fusing about 600 million tons of hydrogen into helium. A tiny fraction of that mass, roughly 4 million tons each second, vanishes into pure energy, according to the relationship E=2. That might sound like a loss, but it is precisely this conversion that powers sunlight. Photons born in the core as high-energy gamma rays take a meandering journey outward, bouncing, scattering, and changing identity countless times. A single photon can take tens of thousands of years to reach the surface, and only 8 minutes more to cross space and arrive at Earth. Along the way, a river of near-massless particles called neutrinos escape straight through the Sun, almost unimpeded, and some pass through your body every second without leaving a trace. By the time sunlight spreads across our planet, it has been softened into the familiar spectrum that blue skies and green leaves know how to use. The warmth on your skin on a bright day is energy released in the Sun's core, long before the first humans looked up to wonder how it all works. The solar surface is not uniformly bright. It is mottled and alive, marked by transient features that reveal the power of magnetism in hot plasma. Sunspots are among the most striking, dark, island-like patches where the gas is cooler by roughly $1,000 to $2,000 degrees than the surrounding photosphere. They're cooler not because the Sun is running out of fuel, but because intense magnetic fields suppress the churning convective motions that normally bring hot material up from below. Sunspots often appear in pairs or groups with magnetic field lines arching between them like luminous bridges in ultraviolet images. They wax and wane over an approximately 11-year cycle, a rhythm driven by the Sun's differential rotation. Its equatorial regions rotate faster than its poles, twisting magnetic fields into knots and loops. When the cycle peaks, sunspots become more numerous, and the Sun's magnetic atmosphere, the corona, grows more dynamic and complex. That complexity can erupt in spectacular fashion. Solar flares are sudden flashes of electromagnetic energy released when stressed magnetic fields in the corona reconnect in new configurations. In minutes, a flare can release as much energy as billions of nuclear bombs. Sometimes the Sun also launches vast clouds of magnetized plasma into space known as coronal mass ejections, CMEs. When one of these coronal storms sweeps across the solar system and encounters Earth's magnetic field, it can rattle our planet's protective bubble and pour charged particles into the upper atmosphere. The result is both beautiful and disruptive. The aurora, the northern and southern lights, blossoms into shimmering curtains of green and crimson as atmospheric atoms and molecules are excited and then glow. At the same time, strong geomagnetic storms can induce currents in long power lines, interfere with radio communication and satellite navigation, and nudge satellites from their orbits. Despite the occasional outburst, the Sun's long story is one of patience and balance. Yet, even patience has an ending. As the core slowly accumulates helium ash, the Sun adjusts. It brightens gradually over hundreds of millions of years. Far in the future, about 5 billion years from now, the core will no longer be able to sustain hydrogen fusion at its center. The Sun will respond by changing its structure. The core will contract and heat. Hydrogen will begin fusing in a shell around it, and the outer layers will expand dramatically. The Sun will swell into a red giant, its surface cooling even as its size increases to many times its current diameter. The innermost planets, Mercury and Venus, will almost certainly be engulfed. Earth's fate is more complicated, but the world we know will long since have been transformed by the Sun's increasing brightness. During this giant phase, the Sun will shed much of its outer atmosphere into space, creating a shell of glowing gas, what astronomers call a planetary nebula, illuminated by the exposed hot core. That core, left behind after the outer layers drift away, will become a white dwarf, a stellar ember roughly the size of Earth, but with about half the Sun's mass. It will no longer fuse fuel. It will simply glow with stored heat, slowly fading over billions and billions of years. The solar system by then, a calmer place of cold remnants and ghostly orbits, will circle a small, brilliant jewel of a star. This is not a tragic ending for our Sun. It is the ordinary, dignified conclusion written by physics for stars of the Sun's mass. The material cast off in the red giant and nebula phases will enrich the interstellar medium, seeding future clouds with the elements our Sun forged during its long, steady life. Somewhere, someday, that matter may become part of a new star, a new planet, and perhaps even new eyes looking up, warmed by a different dawn. For now, our Sun continues its quiet work with a reliability that has framed every human story. Its classification as a G-type main sequence star may sound technical, but it is shorthand for a simple truth. It is stable enough to rise and set through uncounted generations, energetic enough to light oceans and forests, and dynamic enough to remind us in sunspots and auroras that even familiar stars are alive with physics. Each sunrise is a delivery from a nuclear furnace 93 million miles away. Each sunset is a promise that the same light will return. In that rhythm, life learned to flourish. In that light, we learn to see. The discovery of worlds beyond our solar system is one of the most profound achievements of modern astronomy. For centuries, people looked up at the stars and wondered if any of those distant suns had planets of their own. Today, we know the answer. Yes, and more than we ever imagined. Astronomers have confirmed thousands of exoplanets, planets orbiting stars other than our Sun, and suspect that there are billions more waiting to be found. Almost every star you see in the night sky likely hosts its own family of worlds. Some of these planets are gas giants larger than Jupiter. Some are rocky like Earth, and others defy all our expectations. The sheer diversity of these worlds has changed how we see our place in the universe. The solar system, once thought unique, is just one arrangement in a cosmic gallery of endless variety. Finding planets around distant stars, however, is not as simple as pointing a telescope and taking a picture. Stars outshine their planets by enormous factors, millions or even billions of times brighter. So the trick lies in detecting the planet's subtle influence on its host star. One of the most successful techniques is called the transit method. When a planet passes directly in front of its star from our perspective, it blocks a tiny fraction of the starlight, causing a brief, regular dimming. By measuring this dip, astronomers can infer the planet's size, orbit, and sometimes even hints of its atmosphere. The change in brightness is often less than 1%, comparable to a gnat flying across a car headlight as seen from miles away. Yet, modern instruments can detect it with exquisite precision. NASA's Kepler Space Telescope revolutionized this method, observing over 150,000 stars continuously and discovering more than 2,000 confirmed exoplanets. Each small flicker of light in Kepler's data was a clue to another world, silently orbiting far beyond our reach. Among the first worlds discovered were some of the strangest, the so-called hot Jupiters. These are gas giants roughly the size of Jupiter, but orbiting extremely close to their stars. So close that their years last only a few days. Their proximity means their atmospheres are scorched to thousands of degrees, and many are tidally locked, with one hemisphere in perpetual daylight and the other in endless night. For a long time, astronomers hadn't expected such planets to exist. They defied conventional models of planet formation, which suggested that giant planets should only form in the cold, outer regions of a star system. The existence of hot Jupiters forced scientists to rethink those ideas. Perhaps these giants formed farther out and then migrated inward, disturbed by gravitational interactions. Their discovery revealed how dynamic and unpredictable planetary systems can be. Some of these worlds are so inflated by heat that they're puffier than Jupiter, despite having less mass, while others are dense and compact, with metallic hydrogen swirling under crushing pressures. Each one reminds us that the universe is far more creative than our early theories could capture. Beyond the gas giants, astronomers have found a class of planets that seem common yet have no direct equivalent in our own solar system, the so-called super-Earths. These are worlds between Earth and Neptune in size, ranging from about $1.5 to 10 times Earth's mass. Some may be rocky, with mountains, oceans, and atmospheres. Others might be mini Neptunes with thick envelopes of hydrogen and helium. Their diversity makes them some of the most intriguing targets for future study. Many orbit within the temperate zones of their stars, where temperatures could allow liquid water to exist on the surface. In some systems, like the famous TRAPPIST-1, several Earth-sized planets huddle close to a dim red star, all potentially within the right temperature range for life as we know it. These discoveries hint that planets similar to our own may be far from rare. In fact, they may be the most common type of planet in the galaxy. The phrase super-Earth captures both their scale and their promise, a bridge between the familiar and the unknown. When astronomers speak of habitability, they often refer to the habitable zone, the region around a star where conditions might allow liquid water to exist on a planet's surface. Too close to the star and water would boil away. Too far and it would freeze solid. Earth sits comfortably in the middle of our Sun's habitable zone, and water is the key to nearly everything we call life. Our planet's position is an exquisite alignment of chance and physics, but every star has its own version of this zone depending on its brightness and temperature. Around cool red dwarfs, the habitable zone can be so close that planets orbit their stars in just a few days. Around massive, bright stars, it may lie far out, hundreds of millions of kilometers away. Yet habitability is not just about distance. A planet's atmosphere, rotation, and composition all play a crucial role. Venus, for example, sits near the inner edge of our own habitable zone, but is a sweltering greenhouse world. Mars lies near the outer edge and is cold and barren. The habitable zone is therefore a starting point, a map of possibilities rather than a guarantee of life. Still, it gives astronomers a guide for where to look. And missions like the James Webb Space Telescope are beginning to probe the atmospheres of these distant worlds, searching for the chemical fingerprints of water, oxygen, and other gases that might hint at biology. The possibility that we might soon detect an atmosphere altered by life, a faint signature of chemical imbalance, is a quiet source of wonder that drives this entire field of study. The study of exoplanets is still young, yet it has already transformed astronomy into something profoundly personal. For the first time, we can place Earth in a statistical context, one among countless worlds. We've found planets orbiting binary stars, rogue planets drifting alone through interstellar space, and even planets that circle the corpses of dead stars. Each new discovery stretches our imagination a little further, challenging what we think we know about planetary systems and about life itself. Perhaps somewhere orbiting a small red star, in a quiet corner of the galaxy, there is a planet with oceans and clouds, with mountains that cast long shadows at sunset, and with skies lit by a different kind of sun. When we look up at the stars tonight, we now know that many of those distant lights are not solitary at all. Each one may be accompanied by a retinue of worlds, some barren, some stormy, and some perhaps surprisingly familiar. The universe is not made only of stars. It is made of countless places, each with its own story. The age of discovery is far from over. In fact, in the grand scale of time, it has only just begun. The planets of our solar system form a family of worlds that orbit the Sun together, yet each could hardly be more different from the next. Closest to the Sun is tiny Mercury, the smallest planet and one of the most extreme. Because it has almost no atmosphere to trap heat, the temperature on its surface swings wildly, from over 400 degrees Celsius in sunlight to nearly 180 degrees at night. A day on Mercury lasts nearly twice as long as its year, as the planet spins slowly while racing quickly around the Sun. Its landscape is scarred by ancient craters, vast cliffs and ridges left behind when the planet's crust shrank as it cooled. Standing on Mercury, you would see the Sun rise and set twice during a single day, climbing huge and bright over a horizon of rock baked glowing. Despite its proximity to the Sun, Mercury is not the hottest planet. That title belongs to its neighbor, Venus. Venus, the planet named for the goddess of beauty, is a study in deception. Its soft, yellow-white clouds look peaceful from space, but they hide an atmosphere that is more than 90 times denser than Earth's and made mostly of carbon dioxide. The thick clouds trap heat with ruthless efficiency, creating a runaway greenhouse effect that drives surface temperatures to nearly 500 degrees, hot enough to melt lead. Sulfuric acid rains from the upper atmosphere, though it evaporates long before it reaches the ground. Winds there are slow and suffocating, but high above, in the upper clouds, hurricane-speed gales circle the planet in just a few days. Oddly, Venus spins backward compared with most planets, meaning the Sun rises in the west and sets in the east. It is almost Earth's twin in size and mass, but not in temperament, a world that might have been habitable long ago, now locked in a state of eternal, furnace-like calm. Between these two extremes lies our own home, Earth, a planet that seems to strike every balance just right. Its distance from the Sun allows liquid water to exist across much of its surface, and water is the key to nearly everything we call life. Our atmosphere is thick enough to hold warmth, but thin enough to let sunlight through. Oxygen and nitrogen dominate the air, and a gentle layer of greenhouse gases keeps the planet from freezing. Earth's magnetic field shields us from the solar wind, deflecting charged particles that would otherwise strip away the atmosphere, as they have done on other worlds. This magnetic field is powered by the movement of molten iron in the planet's core, a self-sustaining dynamo humming quietly beneath our feet. From orbit, Earth glows in blue and white, alive with clouds and oceans, a rarity as far as we can tell. It is a reminder that while the laws of physics are universal, the outcomes they create can be beautifully singular. Farther out, the red deserts of Mars circle the Sun at a more leisurely pace. The planet is smaller than Earth, but its landscapes are grand in scale. Valleys that dwarf the Grand Canyon, mountains taller than Mount Everest 3 times over, and vast plains of rust-colored dust that shift with seasonal winds. Mars has polar ice caps made of water and frozen carbon dioxide that expand and shrink as the planet tilts through its year. Ancient riverbeds and delta-like formations show that liquid water once flowed across its surface, carving channels and perhaps even forming shallow seas. Today, most of that water is locked underground or frozen at the poles. But robotic explorers have found traces of hydrated minerals and signs that groundwater once bubbled up and evaporated. Mars's thin atmosphere, less than 1% the density of Earth's, leaves it exposed to radiation and temperature extremes, yet it continues to captivate scientists as the most likely candidate for past or even future life beyond our planet. Beyond Mars looms Jupiter, the first of the gas giants and by far the largest planet in the solar system. It is so massive that it could contain all the other planets combined and still have room to spare. Composed mostly of hydrogen and helium, Jupiter has no solid surface, just layers of gas and liquid compressed under staggering pressure. Its cloud tops form colorful belts and swirling storms, the most famous being the Great Red Spot, a vast hurricane larger than Earth that has raged for centuries. Jupiter's immense gravity shapes much of the solar system, pulling comets and asteroids into new orbits, sometimes protecting Earth from impacts and sometimes sending smaller bodies hurtling inward. It has at least 95 moons, including 4 large ones discovered by Galileo in 1610, Io, Europa, Ganymede, and Callisto. Each of these is a world in its own right, volcanic, icy, or oceanic, and some may even harbor the ingredients for life. Jupiter is the guardian and the giant, a planetary king whose influence reaches far beyond its own orbit. If Jupiter is the monarch of the planets, Saturn is the artist. It is adorned with a set of rings so delicate and bright that they are visible even through small telescopes. Composed mostly of water ice mixed with dust and rock, the rings stretch hundreds of thousands of kilometers across, but are often less than a kilometer thick. They're divided into bands and gaps, sculpted by Saturn's many moons, whose gravitational pull acts as a kind of cosmic choreography, keeping the rings sharp and patterned. The planet itself is a gas giant like Jupiter, with a rich atmosphere of hydrogen, helium, and traces of methane and ammonia that form soft bands and swirling storms. Saturn's largest moon, Titan, has a thick orange atmosphere and rivers and lakes made of liquid methane, a world eerily similar to early Earth in chemistry, though far colder. The beauty of Saturn's rings hides their impermanence. Over millions of years, they will gradually fade as particles drift into the planet or out into space. Uranus, farther still, is a planet that redefines what it means to spin. Its axis is tilted by about 98 degrees, meaning it essentially rolls around the Sun on its side. For nearly half of its long 84-year orbit, one pole faces the Sun continuously, while the other remains in darkness. This strange tilt may be the result of a colossal collision early in its history. Uranus is classified as an ice giant with a composition rich in water, ammonia, and methane ices beneath a deep atmosphere. That methane gives the planet its pale blue-green color, serene and ghostly in the dark. Its winds and weather are subtle but complex, with faint cloud bands and occasional bright storms revealed by modern telescopes. Around it circle a set of thin, dark rings and at least 27 moons, each moving in this tilted world like satellites in a skewed orbit. Neptune, the outermost of the major planets, is a deep, vivid blue and home to some of the fastest winds in the solar system, reaching speeds of over 2,000 kilometers per hour. It is another ice giant, similar to Uranus in size but more active, with swirling white clouds and a persistent dark storm called the Great Dark Spot, reminiscent of Jupiter's ancient tempest. Neptune's energy comes partly from internal heat. It radiates more energy than it receives from the Sun, driving the powerful weather that sculpts its atmosphere. Its moon Triton orbits backward relative to Neptune's rotation, suggesting it was once a captured object from the Kuiper Belt. Beyond Neptune lies a frontier of icy worlds and debris, the remnants of the solar system's formation, slowly orbiting in the cold and the dark. Together, these outer planets show the solar system's grand diversity. Gas and ice giants have complex layered atmospheres with storms, bands, and jet streams that span entire hemispheres. Many host elaborate families of moons, some volcanic, some icy, some with hidden oceans beneath their frozen crusts. Their ring systems are dynamic and ever-changing, shaped by small shepherd moons that keep the edges sharp and sculpted through their gravitational influence. Rings are not static ornaments. They're ecosystems of motion with particles colliding, merging and breaking apart in a dance that has lasted for millions of years. The gas and ice giants remind us that not all worlds have solid ground to stand on. Yet each still holds mysteries, beauty, and lessons about how planets and systems like ours come to be. From scorched Mercury to stormy Neptune, the solar system is a microcosm of the universe's creativity, a sequence of experiments in physics and chemistry that produced mountains of rock, oceans of gas, and rings of ice. Every planet is a different answer to the same cosmic question. What happens when gravity and matter have time to play? Moons and ocean worlds remind us that planets are not the only places where fascinating stories unfold. Across the solar system, these smaller companions reveal a hidden richness, from frozen seas beneath their crusts to alien rivers of methane. Flowing through orange haze, even our own moon, silent and grey as it appears, plays an essential role in shaping the conditions that make Earth habitable. Formed roughly $4.5 billion years ago, Likely from debris flung into orbit after a colossal collision with a Mars-sized body, the Moon became Earth's steadying partner. Its gravity tugs gently at the oceans, creating the rhythmic rise and fall of tides that have influenced life for billions of years. Those tides stir coastlines, mix nutrients, and may have provided the shallow, changing environments where early life first adapted to cycles of wet and dry. The Moon also stabilizes Earth's axial tilt, keeping our seasons regular and preventing extreme shifts in climate. Without it, our planet might wobble unpredictably over time, swinging between ice ages and scorching eras. Even now, the Moon slowly drifts farther away, about 4 centimeters each year. But its influence on our world remains profound, both physically and emotionally, as the bright, familiar face that has guided countless generations through the night. Beyond Earth, the gas giants host their own remarkable moons, many of which hold secrets beneath their frozen shells. Around Jupiter orbits Europa, one of the most intriguing worlds in the solar system. At first glance, it seems like a smooth, icy sphere crisscrossed with brownish-red lines and cracks. But those markings hint at something extraordinary beneath. A global ocean of liquid water kept warm by tidal flexing as Jupiter's immense gravity kneads the Moon's interior. That constant squeezing and stretching generates enough heat to prevent the ocean from freezing solid. Even though Europa's surface temperature hovers around 160 degrees Celsius, the ice above is thought to be tens of kilometers thick, floating atop a vast salty sea that may contain twice as much water as all of Earth's oceans combined. Occasionally, plumes of vapor have been observed erupting from the surface, possibly venting from this hidden ocean. Scientists dream of one day sending a probe to pierce the ice and explore the waters below, searching for signs of life that might have evolved in darkness, nourished by heat and chemical energy rather than sunlight. Saturn, too, has its share of wonders, and among them, Enceladus stands out as a tiny moon with an outsized secret. Barely 500 kilometers across, it gleams like a perfect white pearl against the blackness of space. Beneath that pristine surface lies another global ocean warmed by tidal forces from Saturn's immense gravity. Near the South Pole, enormous fractures known as tiger stripes vent jets of water vapor, ice particles, and organic compounds into space. These plumes were discovered by the Cassini spacecraft, which flew through them and directly sampled their composition. What it found astonished scientists: complex organic molecules, salts, and evidence of hydrothermal activity at the ocean floor, conditions remarkably similar to those found around Earth's deep-sea vents, where life thrives without sunlight. Enceladus, once thought to be an inert ice ball, turned out to be geologically active and potentially habitable. The material it sprays into space even contributes to Saturn's faint E-ring, meaning this tiny moon is literally feeding a ring system as it vents its secrets into the void. Another of Saturn's moons, Titan, offers a very different kind of world. It is the only moon in the solar system with a thick atmosphere, denser even than Earth's, composed mostly of nitrogen with traces of methane. From orbit, Titan looks like a hazy orange sphere, its surface hidden beneath layers of smog-like clouds. Yet, radar and infrared mapping have revealed an astonishing landscape below. Lakes, rivers, and seas, not of water, but of liquid methane and ethane. These hydrocarbons fill basins, carve channels, and evaporate into the sky, forming a complete weather cycle much like Earth's, but with methane playing the role of water. Titan's temperature hovers around 179 degrees Celsius, cold enough to keep methane in liquid form. On the surface, dunes of dark organic sand stretch for hundreds of kilometers, and icy rocks made of water are as hard as granite. It is a world where chemistry has taken strange turns, and where scientists wonder whether exotic forms of life could exist, not in water, but in liquid hydrocarbons. In the far future, when the Sun swells into a red giant and warms the outer solar system, Titan may become temperate, a brief, distant echo of habitability. Among Jupiter's many moons, one stands apart for its sheer size and strength. Ganymede, larger than Mercury and nearly as big as Mars, is the solar system's largest moon and the only one known to have its own magnetic field. This magnetic bubble, weak but significant, interacts with Jupiter's immense magnetosphere, creating shimmering auroras that dance around its poles. Ganymede's surface is a patchwork of bright and dark regions, ancient cratered terrain mixed, with younger grooved plains where ice once shifted and refroze. Beneath its icy crust lies yet another hidden ocean, possibly sandwiched between layers of ice under immense pressure. The presence of a magnetic field suggests a liquid metallic core, meaning Ganymede is not a frozen relic, but a differentiated world with a complex interior. Like Europa and Enceladus, it may harbor conditions suitable for life, though its deep layers would be difficult to reach. Still, its size, structure, and magnetic personality make it one of the most fascinating worlds in the solar system. Taken together, these moons and ocean worlds show that our solar system is far more active and diverse than once imagined. For centuries, astronomers saw moons as mere companions to planets, cold, inert satellites circling larger bodies. Now, we know they can be dynamic worlds in their own right, with weather, oceans, volcanoes, and magnetic fields. Some may even hold environments where life could arise independently of sunlight, drawing energy instead from chemistry and heat. From the tides of our own moon to the geysers of Enceladus and the methane rivers of Titan, these places challenge our imagination and expand our definition of what a habitable world might be. It's possible that the first discovery of extraterrestrial life, if it happens within our solar system, will not come from Mars or any planet at all, but from a moon orbiting quietly in the cold, carrying an ocean beneath its frozen shell. Asteroids, comets, and meteors are the small wanderers of the solar system. They are ancient fragments and icy messengers that carry within them the memory of creation. They are the leftovers of planetary construction, the debris that never coalesced into full-fledged worlds. Between Mars and Jupiter lies the asteroid belt, a vast region where countless rocky bodies orbit the Sun like a cosmic junkyard, frozen in time. Most are no larger than mountains, but together they tell the story of a planet that never formed. Jupiter's immense gravity prevented these pieces from merging, constantly stirring and scattering them over billions of years. The belt stretches millions of kilometers wide, yet is surprisingly sparse. If you were to fly through it, you would almost never see another asteroid close by. Still, a few stand out. Ceres, a dwarf planet nearly 1,000 kilometers across, Vesta with its colossal impact crater, and Pallas tilted oddly on its side. These worlds are survivors from an era when collisions and chaos shaped everything. Some asteroids are metallic, the exposed cores of shattered protoplanets. Others are carbon-rich and dark, like lumps of cosmic coal. Together they preserve the conditions and chemistry of the solar system's infancy, long before the Earth solidified. Comets are even older and more mysterious. They come from the cold outskirts of the solar system, where ices of water, methane, and ammonia remain frozen for eons. When a comet's elongated orbit brings it near the Sun, the heat awakens it. Ice begins to vaporize, releasing jets of gas and dust that form the comet's glowing coma and sweeping tails. The sight of a comet with its luminous streak arcing across the night sky has fascinated humans since prehistory. Every comet grows two tails, one of dust, reflecting sunlight in a golden arc, and another of ionized gas, glowing faintly blue as it is pushed straight outward by the solar wind. Each pass near the Sun reshapes the comet, eroding its surface and leaving trails of debris behind it. Eventually, many comets break apart entirely, scattering their icy fragments through space. Some originate in the Kuiper belt beyond Neptune, while others are thought to come from the far more distant Oort cloud, a spherical shell of icy bodies that may extend halfway to the nearest stars. These frozen travelers are time capsules, preserving the volatile ingredients that helped seed the early Earth with water and organic molecules. When these fragments cross Earth's path, they light up our skies as meteors, tiny specks of dust and rock burning brilliantly as they streak through the atmosphere. Most are no larger than grains of sand. Yet the friction of their passage compresses and heats the air ahead of them so fiercely that they flare for a brief instant, leaving glowing trails before disintegrating. The word meteor comes from the Greek for thing in the air, but some survive the plunge all the way to the ground. Those survivors are called meteorites. They're among the most precious scientific specimens on Earth, pieces of other worlds that fall into our hands. Some are metallic, composed mainly of iron and nickel. Others are stony, rich in silicates and carbon compounds. A few even contain tiny mineral grains older than the solar system itself, formed in ancient stars and carried here across light years of space. When scientists slice open a meteorite, they're holding not only rock, but history, the raw material from which planets like ours were built. Every year, the Earth encounters several regular meteor showers when our planet's orbit crosses the dusty paths left by comets. The Perseids in August, the Geminids in December, and the Leonids in November are among the most famous. During these events, dozens or even hundreds of meteors can be seen each hour, all appearing to radiate from a single point in the sky. These showers are cosmic maintenance events, reminders that our planet moves through an environment rich with leftover debris. Each streak of light is a momentary connection between our world and the vastness beyond, a grain of comet dust meeting an atmosphere thick with life. Over time, the dust from such encounters settles gently onto Earth's surface, adding hundreds of tons of extraterrestrial material each day. Some of that comet dust carries carbon and organic molecules, the same ingredients that may have contributed to the emergence of life billions of years ago. Asteroids in their quiet orbits also have a more dramatic side. Occasionally, their paths are nudged by gravitational resonances with Jupiter or by collisions with one another, sending one on a trajectory that crosses Earth's orbit. Most of these near-Earth asteroids pass harmlessly by, but a few have struck our planet in the deep past, reshaping its history. The impact that ended the age of the dinosaurs 66 million years ago was caused by an asteroid roughly 10 kilometers wide, striking with the energy of billions of atomic bombs. Such events are rare, but they serve as reminders that even small celestial bodies can have enormous consequences. For this reason, scientists track the orbits of thousands of near-Earth objects, mapping their paths centuries into the future. What makes these rocky and icy remnants so captivating is not just their danger or beauty, but their age. Many asteroids and comets are essentially unchanged since the solar system's earliest days, over $4.5 billion years ago. Their minerals and isotopes carry the chemical fingerprints of the nebula that gave birth to the Sun and planets. In studying them, scientists glimpse a time when our world was still a disk of dust and gas swirling around a newborn star. Spacecraft have even brought back samples directly from asteroids, allowing us to touch matter that predates the Earth itself. Each flake of dust, each icy shard is a messenger from that ancient time, a reminder that the story of our planet began long before there was an Earth to tell it. In the grand sweep of the solar system, asteroids, comets, and meteors are its storytellers. They drift silently through space, preserving memories of the moment when everything began. Some burn brightly for a heartbeat and vanish. Others wander for billions of years, unchanged. They are the seeds and the scars of creation, connecting our brief lives to the deep, slow processes that built the planets. The next time you see a meteor streak across the sky, think of it not as a fleeting light, but as a visitor from the dawn of time, a tiny traveler carrying with it the ancient dust of stars. Gravity and orbits weave the choreography of the cosmos, the invisible rhythm that keeps planets, moons, and stars in their eternal dance. Every object in space is falling, and yet almost none of them ever hit the ground. That paradox lies at the heart of orbital motion. When something moves fast enough sideways while falling, it continually misses the surface it's falling toward. That's what an orbit is, a continuous state of free fall curved by gravity. The Moon, for example, is always falling toward Earth, but its sideways speed ensures that as it falls, Earth's surface curves away beneath it. The result is a graceful, endless loop, neither collision nor escape, but perpetual motion. The same principle holds for planets around the Sun, satellites around planets, and even galaxies circling one another. Gravity doesn't simply pull things together. It shapes the pathways along which everything moves, sculpting the grand architecture of the universe. The elegance of these motions was first captured in the early 17th century by Johannes Kepler, who distilled the complex movements of planets into three simple laws, turning celestial motion from a mystery into a mathematical harmony. Later, Isaac Newton explained why they worked. Gravity was the universal force that governed not only apples falling to Earth, but also moons circling planets and planets circling stars. With that insight, the heavens and the Earth were united under one elegant principle. Yet gravity's influence doesn't end with smooth orbits. It also orchestrates resonances, special relationships where orbital periods form neat ratios. When two moons, planets, or asteroids orbit in resonance, the gravitational tugs line up in a repeating pattern, like dancers keeping step in rhythm. This can have both stabilizing and destabilizing effects. For instance, Jupiter's moons, Io, Europa, and Ganymede, are locked in a 1-2-4 resonance. This pattern keeps their orbits perfectly balanced and also generates internal heat through tidal flexing, powering Io's volcanoes and Europa's subsurface ocean. In other cases, resonances can create chaos. In the asteroid belt, certain regions are empty because asteroids there once shared orbital periods that matched resonances with Jupiter's gravity. The repeated tugs destabilize their paths, flinging them into new orbits or out of the belt entirely. These Kirkwood gaps are scars of resonance, places where harmony gave way to disruption. Within that gravitational clockwork, there exist points of delicate balance known as Lagrange points. These are spots in space where the gravitational pull of two large bodies like Earth and the Sun perfectly balances the orbital motion of a smaller object. At these points, a spacecraft can effectively hover, maintaining its position with minimal fuel. L1 sits between Earth and the Sun, an ideal vantage point for solar observatories. L2 lies just beyond Earth's orbit, shielded from direct sunlight, perfect for telescopes like the James Webb Space Telescope. These balancing spots are cosmic rest stops, places where gravity and motion hold one another in near-perfect equilibrium. Gravity's reach extends even to the tiniest motions and the most intimate effects. When one object exerts a stronger pull on one side of another than the other side, tidal forces arise. On Earth, these forces from the Moon and the Sun lift and lower our oceans, creating the rhythmic tides. But tides don't only move water, they also sculpt moons and planets. When gravity stretches a moon's interior, it generates frictional heat. This process, called tidal heating, can keep distant worlds warm long after their formation. Jupiter's moon, Io, is the most dramatic example, driven by tidal flexing that melts its interior, creating hundreds of active volcanoes. Europa itself, though encased in ice, is warmed enough to sustain a liquid ocean beneath its surface. Understanding orbits and gravity means seeing motion as the natural state of the universe. Everything falls, everything moves, everything responds to the curvature of space and time. The same principle that keeps the Moon circling Earth also governs the swirl of galaxies, the arcs of comets, and the graceful paths of spacecraft navigating between worlds. To watch a satellite glide across the night sky is to witness gravity and motion in perfect partnership, an invisible conversation between mass and energy that stretches from your backyard to the edges of the cosmos. And while orbits may seem precise and mechanical, they are also deeply poetic, eternal loops of falling and missing, of attraction and escape. Gravity doesn't simply hold the universe together. It gives it rhythm, shaping the patterns by which worlds and stars perform their endless, silent dance through time. And that brings us to the end of tonight's quiet journey through the universe. From the silence of deep space to the restless hearts of stars, and from invisible dark matter to the hum of the cosmic microwave background. We have drifted across billions of years and trillions of miles, only to find that the vastness is reflected in the tiny atoms that compose us. If you've made it this far, I hope you're feeling just a little more connected to the expanse above, and perhaps a little more peaceful too. We've touched on the unseen architects of reality, the gravity, the dark energy, and the quiet forces that ensure that even in the ultimate emptiness, balance is maintained and new light is always being born. This realization that you are made of the same ancient dust and governed by the same steady laws that guide the galaxies should be profoundly comforting. If you enjoyed this exploration, a simple like genuinely helps more than you might think. It tells the algorithm that this kind of calm, thoughtful science is worth sharing, and it helps other curious minds find their way here. And if you'd like to join more of these gentle cosmic wanderings, you can subscribe to The Whispering Scientist and tap the notification bell so you'll be the first to drift off to the next story from space. Until then, thank you for watching, for listening, and for sharing a few quiet moments beneath the stars. Sleep well, and may your dreams drift somewhere between the atoms and the galaxies.